from low-bit quantization to discrete diffusion and weakly supervised reasoning. Today's papers all tackle the same question from different angles. How do we make AI systems smarter, faster, and more reliable under real-world constraints? We'll look at a new quantization method that brings LLMs closer to vector-quantized accuracy without losing kernel efficiency, a reinforcement learning breakthrough that stabilizes text-to-image diffusion models, and fresh evidence on when weak supervision can truly teach language models to reason. Stay with us for the key ideas and surprising results. Let's explore the first paper, GSQ Highly Accurate Low-Precision Scalar Quantization for LLMs via Gumbel Softmax Sampling. GSQ, Gumbel Softmax Quantization, reframes post-training weight quantization as differentiable discrete assignment over scalar grids, replacing greedy rounding with per-coordinate Gumbel Softmax sampling jointly optimized with groupwise scales. Unlike GPTQ, AWQ, or efficient QAT, GSQ keeps a fully standard symmetric scalar format, so it is drop-in compatible with existing inference kernels, yet it narrows most of the accuracy gap to vector-quantized methods such as QTIP, QUIP number, He-Fi tuning, and GPTVQ. The key novelty is a tight relaxation matched to low-bit cardinalities. Ternary and 2-bit grids use full per-level logits, while 3-4 BPP settings use a local shift parameterization with only 5 logits per weight coordinate, reducing the search space from 2 B candidates to nearby moves around a GPTQ warm start. Training uses anneal temperature, Gumbel noise, line optimization, and gradient accumulation as variance reduction. GSQ also supports non-uniform layer-wise bit allocation on Llama 3, 1, 8B, Instruct, and 7.0b. Instruct, GSQ improves average zero-shot accuracy over the best scalar baseline, efficient QAT, by 4.76 and 4.14 points at 2 bitses respectively, while trailing QTIP by only 1.33 and 1.68 points. At 3 bitses, it matches or exceeds all scalar baselines and is essentially tied with QTIP on 70B. Ternary GSQ already beats higher bit scalar baselines on 8B. With humming kernels on NVIDIA L40S, 2-bit GSQ reaches 6.2 times throughput over BF16 and mixed to 37 halves, 6 2-bit configurations, deliver 5.46 times 4.99 times speedups. GSQ also scales to trillion parameter MoE models. On Kimi K25 2-bit GSQ preserves or improves Math 500 and Live Code Bench v6 while degrading GPQA Diamond, attributing sensitivity to calibration data mismatch. Let's explore the second paper, UDM GRPO Stable and Efficient Group Relative Policy Optimization for Uniform Discrete Diffusion Models. UDM GRPO is the first reinforcement learning framework for uniform discrete diffusion models in text-to-image generation. The key failure mode of a naive flow GRPO adaptation is severe optimization collapse within about 500 steps with oscillatory rewards and exploding KL divergence. The paper identifies 2 causes. Intermediate denoising outputs are too noisy to serve as policy actions, and optimizing on reverse sample trajectories creates an out-of-distribution mismatch versus pre-training. UDM GRPO fixes both by redefining the action as the final clean sample x1 at every time step, and by reconstructing RL trajectories through the forward diffusion process x forward rather than the model's backward trajectory x backward. This keeps the policy update aligned with the pre-trained probability path and stabilizes GRPO on discrete token states. The method is built on a 1, 7, B parameter URSA-based model and further adds reduced step optimization, which trains only on 3 consecutive early high noise time steps, and CFG-free training, which removes classifier-free guidance during RL to lower compute and widen exploration. On Genival, URSA improves from 0.69 to 0.96 overall accuracy, with 1 object, 2 object, counting, colors, position, and attribute binding all reaching 1, 1, 0.95, 0.97, 0.97, and 0.85 respectively. Pick score rises from 21.79 to 23.81, and OCR increases from 0.08 to 0.57. Ablations show that using X1 instead of XT1 improves stability, forward trajectories outperform backward ones, and CFG-free converges faster with lower KL. The approach also transfers to Fudoki, raising GenEvol from 0.76 to 0.86 and PIC score from 21.32 to 23.4. Let's explore the third paper. When can LLMs learn to reason with weak supervision? This paper studies RLVR under weak supervision across Qwen 2, 5, and Llama 3. Two models on math, science, and graph reasoning with GRPO using scarce data, corrupted labels, and proxy rewards. The central empirical result is that generalization is controlled by reward saturation dynamics. Models that sustain a long pre-saturation phase improve on both training reward and downstream accuracy, while rapidly saturating models memorize and then plateau. In the 8 sample regime, Qwen 2, 5, Math 1, 5B sustains training for over 300 steps and transfers to held-out benchmarks, whereas Llama 3 to 3B, Instruct, saturates within roughly 55-61 steps and fails to generalize. The key predictor is not output diversity, but reasoning faithfulness, defined as whether intermediate steps logically support the final answer. Llama often has higher semantic diversity, yet lower faithful reasoning, indicating diverse but unsupported chains. Under noisy rewards, Qwen Math and Qwen Science remain robust up to 70% label corruption, while Llama and Qwen on graph degrade at 50% corruption. Pure proxy rewards such as self-certainty and majority vote usually collapse or reward hack with only Qwen 2, 5. Math showing partial stability under majority voting. The strongest intervention is pre-RL training. Continual pre-training on 52B Nemotron CC math tokens, plus supervised fine-tuning on 43. 5K explicit reasoning traces, thinking SFT, raises faithfulness, extends the pre-saturation phase, and restores generalization for Llama 3, 2, 3B across all weak supervision settings. Non-thinking SFT on final answers alone is insufficient. That's a wrap on today's AI paper highlights. Thanks for watching.